For centuries, humanity has searched the heavens for worlds beyond our own, new planets orbiting distant suns, potential homes for life scattered across the vastness of the galaxy. From Galileo's first glimpse of Jupiter's moons to the Kepler Space Telescope's breathtaking catalog of thousands of exoplanets, our quest has been relentless. But now, a new explorer has joined this cosmic journey, one not made of flesh and bone, but of code and computation. Artificial intelligence, the digital mind humanity has built in its own image, is learning to see the universe in ways no human ever could. AI doesn't tire. It doesn't blink. It can sift through terabytes of data from telescopes, satellites, and simulations, uncovering faint signals that human eyes might never notice. It finds patterns hidden in the noise, the whisper of a planet's transit, the tug of unseen gravity, the dimming of a distant star. This marks a turning point in astronomy, a revolution not of telescopes or rockets, but of perception. Machines are becoming our partners in exploration, extending our senses across the cosmos. Through their algorithms, we are training a new generation of explorers, capable of identifying planets light years away and perhaps even detecting signs of alien life. But how did we arrive here? How did artificial intelligence become the newest tool in the oldest of human pursuits, the search for other worlds? The early 21st century ushered in a golden age of planet hunting. NASA's Kepler mission, launched in 2009, transformed our understanding of the galaxy. For nearly a decade, Kepler stared at a single patch of sky, recording the brightness of over 150,000 stars. Its mission was simple yet profound. Watch for the tiny dips in starlight that occur when a planet passes in front of its star, a cosmic shadow known as a transit. The data Kepler returned was immense, millions upon millions of light curves, each representing a star's flickering brightness over time. Hidden within these curves were the signatures of distant worlds, some large and obvious, others subtle, lost in the noise of stellar activity, cosmic rays, or instrumental error. Human astronomers spent years sifting through this deluge, identifying exoplanet candidates by eye and algorithm. But the sheer volume of data soon exceeded human capacity. Even teams of experts could miss the faintest, most delicate signals. Worlds smaller than Earth, orbiting dim or variable stars. That's when artificial intelligence entered the picture. Neural networks, modeled after the human brain, were trained on thousands of confirmed exoplanets, learning to recognize the subtle fingerprints of a planet's transit. Unlike traditional algorithms, these AIs didn't just follow instructions. They learned. They adapted. They improved. In 2017, a neural network developed by Google AI and NASA's Kepler team made headlines. It discovered 2 new exoplanets, including one orbiting Kepler, 90, a star already known to host 7 planets. The find confirmed Kepler 90 as the first star system discovered with as many planets as our own solar system. And it was AI that found the missing world, a discovery hidden in plain sight, overlooked by humans. That moment marked the dawn of a new partnership between human curiosity and artificial cognition, a synergy that continues to redefine what it means to explore the universe. At the heart of AI's power lies its ability to detect the faintest traces of order amid chaos, to recognize patterns invisible to human intuition. When applied to astronomy, these algorithms become something extraordinary, a kind of machine vision capable of perceiving the faint pulse of distant planets across the noise of cosmic data. Machine learning systems are trained on immense data sets of known stellar behavior, brightness variations, noise profiles, and confirmed planet transits. Over time, They learn to distinguish between true planetary signals and false positives caused by binary stars, cosmic rays, or instrumental glitches. Deep learning models, like convolutional neural networks, excel at identifying the specific shapes and timings of transit events. Others, using probabilistic reasoning and Bayesian methods, estimate the likelihood that a signal truly represents a planet. Together, these techniques can process thousands of light curves in seconds, a task that would take humans months or years. But AI does more than detect, it predicts. It can simulate potential orbital configurations, reconstruct missing data, and even suggest where to point future telescopes. As data pours in from new missions, like TESS, Cheops, and the upcoming Plato Observatory, AI's role becomes indispensable. And beyond the transit method, artificial intelligence is branching out. It is learning to detect exoplanets through gravitational microlensing, where a star's light is bent by the gravity of an unseen planet. It analyzes the wobble of stars using radial velocity data, revealing planets that never transit their suns. Even the faintest atmospheric signatures, chemical traces of oxygen, methane, or water, are being sought by AI-driven spectroscopic analysis. These are not merely numbers to an algorithm. They are fingerprints of potential life, waiting to be matched and understood. In this new age of discovery, artificial intelligence doesn't just process data, it interprets it. It begins to glimpse the universe as a tapestry of possibilities, turning faint whispers of light into stories of worlds we have yet to visit. What happens when we hand the search for life itself to our digital counterparts? As our telescopes grow more powerful and our data more complex, human intuition alone cannot keep pace. AI is becoming not only a tool for detection, but an interpreter of habitability, analyzing the environments of newly found worlds to judge whether life might exist there. By combining data from exoplanet catalogs, stellar models, and atmospheric simulations, artificial intelligence can estimate whether a planet falls within its star's habitable zone, the region where liquid water could exist. It can assess the stability of orbits, the likelihood of protective magnetic fields, and the presence of essential elements like carbon, hydrogen, nitrogen, and oxygen. In some cases, AI even suggests where not to look, teaching us efficiency by identifying false leads, refining our search strategies, and highlighting worlds most likely to yield profound discoveries. Beyond exoplanets, AI is helping astronomers re-examine data from our own solar system. Machine learning has identified potential cryovolcanic activity on icy moons, mapped methane plumes on Mars, and detected subtle chemical patterns on Titan and Europa, all potential signs of geological or even biological processes. The future promises even greater possibilities. Imagine autonomous observatories, AI-controlled telescopes that continuously scan the heavens, learning from every frame they capture. Imagine spacecraft equipped with onboard AI, capable of making real-time decisions, identifying new planets, or adjusting trajectories to study unexpected phenomena. In this unfolding narrative, AI becomes more than an assistant. It becomes an explorer in its own right, a synthetic intelligence expanding humanity's reach into the cosmos. The age-old question of, are we alone, may one day be answered not by human eyes, but by the analytical gaze of an artificial mind. As we gaze into the night sky, our imagination fills the darkness with wonder. For generations, we have dreamed of other worlds, of oceans under alien suns, of skies painted by unfamiliar constellations. Now, through the partnership of human ingenuity and artificial intelligence, we are beginning to find them. AI extends our senses into realms we cannot reach, allowing us to see further, faster, and deeper than ever before. Yet, behind every algorithm lies a spark of human curiosity, the same drive that once led sailors across uncharted oceans, now encoded in lines of digital thought searching the stars.